behind the scenes. It will help you figure out how to do these computations. Okay? I don't claim that today's lecture is the most thrilling lecture you will ever attend in your life. So, there's my release. You're bored. Anyway, but it's important stuff. Okay? So, what we're going to be talking about for the next few classes are normal distributions. Okay? And what I'm going to tell you is the following. Well, I'm going to tell you many things. But to begin with, the distribution of a data set measures the frequency in which each data point occurs. Check this out. You can't really see this thing too well, but I'll draw it in. All right. Well, what I have here, and if you guys can't read it in the back, don't worry about it. I'll draw over this and show you the scoop of what's going on. I claim that each of these guys are frequency distributions. Okay? In case you can't read in the back, what this is its percentage of the population with given IQ scores. So down here are various IQ scores, and this is the percentage of the population that has those. Isn't this pretty? I think so too. All right, next. This one is the percentage of families with given incomes. So down here it's incomes in thousands of dollars, and this is the percentage of the families. So just over 8% of the families make less than $10,000 per year. Whoa, look at all these families. Like over 10% of the families make between $100,000 and $150,000 a year. Okay, so do you see how these are like the histograms that I mentioned earlier? Okay? That's essentially what we're going to be talking about, but we're going to be talking about specific type. These are the percentages of Americans of a given age, so these are various age brackets, and these are the percentages of the population that have them. And then these are birth weights in kilograms and the number of births. Okay? So essentially what we're saying, like right here is, okay, just over 7% of our population, it has involves people between the ages of 5 and 9. Okay? You guys with me here? Cool. So, those are what we're looking at when we talk about distributions. Now, two of these guys are what we're particularly interested in. I claim it's these two. These are kind of random all over the place, but aren't these pretty little graphs here? Okay? Those are called bell-shaped curves. And that's actually the characteristic sign of having a normal distribution. Okay? So, when our curve is bell-shaped, and that is precisely what our normal distributions look like. I would imagine you guys have heard of normal distributions before, or things on a bell curve. If you haven't, once you get into the area of your study, I'm absolutely certain, especially if you're in social science, that you're going to be coming up against normally distributed data. What you're going to see on Friday and Monday and from here on out is normal distributions come up in the strangest of places. Okay? So, there's some important features that I would like to mention of our normal distributions. The first one is that your mean is equal to your median. Okay? In other average of all of your data points, it happens to be your middle data point. Because isn't that precisely what your median is? Okay, so your mean and your median are exactly the same. Okay? Another really cool feature is that most of your data is clustered about your mean. We can look over here at this example. Okay, the mean IQ is 100. Wouldn't you guys agree that most of your data is around 100? Right, because it gets shorter and shorter as you get away from 100. You guys with me? Right, as you get bigger, it gets smaller, and it gets smaller. The percentage also gets smaller. And the third one that I would like to mention is that your bell curve is symmetric about the mean. If you aren't sure what that means, don't worry. I'll tell you once you have it written down. When I think of symmetry, I think of butterflies. Okay? Butterfly wings in general are mirror images of each other. Essentially, when you say that a graph is symmetric about the mean, what you're saying is, hey, if you draw a vertical line through your mean, isn't one side a mirror image of the other side? Okay? So what does that tell us about our data distribution? Okay, if this is my middle and one side is a mirror image of my other side, do you guys agree that 50% of the data is above the mean and then the other 50% of the data is below the mean? Okay, it's kind of like your halfway point through your graph. Are you guys with me this far? Okay, well, some other really cool things about this. It turns out that for a normal distribution, the mean and the standard deviation completely determine the bell shape. So we didn't just talk about standard deviation just so that I could have you guys do a bunch of nasty computations. Okay, the standard deviation is actually most important in this section. All right, so let's look at the bottom two graphs here. Okay? First off, let me ask you guys to remember what your standard deviation measures. Doesn't your standard deviation measure the spread of your data from your mean? You guys want me to write that down? Yeah? Okay. So, recall, the standard deviation is a measure of the spread of the data about the mean. So what does that tell us? Well, it tells us that if we have a small standard deviation, isn't most of our data clustered very close to our mean? Whereas if our standard deviation is larger, our data is more spread out. Okay? So let me show you an example. Here are two graphs. They both have a mean of 500. Okay? But I claim that this graph here, comparatively, has a large standard deviation, and this graph here has a small standard deviation. Why? Because remember, the height of the graph expresses the frequency, and isn't your data a lot more spread out here, whereas here it's a lot more compact. Okay? So when you have a large standard deviation, you're going to have more of like a wide bell shape. Whereas when your standard deviation is small, you're going to have a thin or a steep bell shape. Does that make sense? All right. So, one of the other things that I would like to mention is called a rule of thumb. These are not numbers that I require you to memorize, but I think it's really interesting factoid. And what it is the following. Okay? The rule of thumb says if a data set is normally distributed, you guys, heights, weights, IQs, all sorts of different things are normally distributed. It's pretty cool. Okay, but if a data set is normally distributed, 68% of the data lies within one standard deviation of the mean. And this holds whatever your standard deviation is, because you're going to just be adding and subtracting a different number. Okay? So, that says that over 2/3 of your data is right within one standard deviation of the mean. Now, what does it mean to be within one standard deviation of the mean? Excuse the redundancy. It means that you can take the mean plus your standard deviation, or your mean minus your standard deviation, and your data is going to fall within that interval. Okay? The other rule of thumb says that 95% of the data lies within 2 standard deviations of the mean. And from that, what you do is you take your mean minus 2 times your standard deviation, and your mean plus 2 times your standard deviation. So according to this graph over here, being within 2 standard deviations of your mean, 95% of your data is in that range. And the last rule of thumb, again, you don't have to have this 68, 95, 99.7 rule memorized, but 99.7% of the data lies within 3 standard deviations of the mean. So virtually, nearly all of your data falls in that range. So here's about 99.7% of your data. And this value is your mean minus 3 times your standard deviation. And this value is your mean plus 3 times your standard deviation. Okay? So that is one really, really cool thing to note. Now, when used as a unit of measurement in this way, so when used as a unit of measurement, in this way, the standard deviation is often referred to as the z-score. So when we're dealing with normal distributions, we like to talk about how many standard deviations away from the mean something might be. And when we do that, it has that term called your z-score. It's a term you need to know only insofar as if I ask you to find the z-score, you probably want to know what I mean. 4 years ago by now. I remember there was a case that was brought up to the Supreme Court, and it involved the death penalty. You see, the death penalty in the states that allow it, the Supreme Court put a ruling on it, okay? You cannot impose the death penalty, and I can't remember whether it was 2 or 3 standard deviations below the mean, but what they said is, hey, if somebody's IQ is, I believe it was 2 standard deviations, is below 2 standard deviations below the mean, you are not allowed to use the death penalty. What you can do is toss them in jail for the rest of their life, but when you're 2 standard deviations below the mean, the Supreme Court rules that you're not mentally competent in order to understand the nature of the crime committed, and therefore they can't pursue the death penalty. And I believe it was a case in Florida where this guy was kind of borderline, and so it went all the way up there. Yeah?
So they word it in such a way so that the mean changes a lot.
The mean doesn't really change.
So what's that? Say it's going to modify %.
Equivalent, but it depends upon what the IQ mean is. Usually they say the mean is 100, but the standard deviation might change from population to population. Okay, so you can compute the mean and the standard deviation for one population, but that might be different than for another population. I don't really know the correct wording, but I remember seeing that this went to the Supreme Court, and they talked about the standard deviations below the mean. I'm like, oh, cool. Except it wasn't cool, right? Because it was right. But anyway. All right. Now, let me make a comment responding to this. Okay? The Z-score for a data point is precisely the number of standard deviations that the point lies either above or below the mean. For those points above the mean, your Z-score is positive. For those points below the mean, your Z-score is negative. So the sign of your Z-score will tell you whether it's greater than or less than your mean. Okay? Now, one other piece of terminology, and then we'll get to be a little more pragmatic and do some things here, is, I'm sure you've all heard of this, the percentile for a number relative to a list of data is precisely the percentage of data points that are less than or equal to that point. And you guys have probably heard of this. For example, if you had to take the ACT or the SAT in order to get into the school, not only do you get a score, but you get a percentile. And you might take your ACT like 2 times. And you could get the exact same score both times, but that does not mean that your percentile is the same both times. The key thing to remember is that the percentile is relative to the list of data at that point. So for example, maybe you got like a 32 on your ACT, but in one place you scored in the 90th percentile, and another time it was the 80th percentile. Okay? That's because they are comparing you to all the other folks who are taking the test at that time. So, For example, I mentioned the 90th percentile. What does that mean? That means that you scored better than or the same as 90% of all those other folks who did the same thing. I claim that to be in the 90th percentile also means that you're in the top 10%. You guys see how that follows? Okay, if you're in the 90th percentile, you got some bragging rights there. You want me to move this down? Are you with me? Okay, cool. On the other hand, if you score in the 20th percentile, that's kind of a bummer situation, right? You don't want to brag, yeah, I'm in the top 80%. I mean, it's good to be in the top 80%, but it's better to be in the top 10%. So is everybody okay with this percentile business? We're going to be using this soon enough. Okay? All right. So one more quick comment that I want to make is the following. And then we shall play. Often, guys, what we're going to be given is got a little bell-shaped curve. Right smack dab in the middle is our mean. Now, as a reminder, you guys remember, I said we use the Greek letter mu for our mean, and we use sigma for the standard deviation. We're going to start abbreviating those a lot more, okay? So, smack dab in the middle, pretend that really is smack dab in the middle. There's our mean, okay? And it doesn't really matter what we're looking at this point, but suppose, for example, I wanted to find the probability that a data point lies, say, right in here, between these two values, A and B. Okay? That's very often what we're going to want to do here is find the probability that our data point lives somewhere. Okay? The way I would write that is I want to find the probability that my value of X lies between A and B. Do you agree on wanting to find the probability that it lies within what I've colored red? Okay? Now, one of the things that is super cool, it's beyond the scope of this class for me to prove it to you. You use calculus. Does anyone in here study calculus? If you have, do you remember Riemann sums? Areas under curves? Anyway, you use calculus in order to do that. But you guys who have not had calculus, don't sweat it. We're not doing any calculus in this class, which is actually rather unfortunate. But it turns out that the probability, for example, a data point lies in a region is precisely the area under our curve in that region. So it turns out, you guys, that the probability that a data point lives in this region is precisely the area under the curve in this region. Don't worry, you're not going to be doing any geometry. Your calculator knows how to compute those areas. Okay? I warned you it was kind of dry, right? Okay. Alrighty. So, for example, we might want to find the probability that a particular x value lives between A and B. Maybe we want to find the probability that our x value is greater than B. Wouldn't that be this region right here? Another thing we might want to do is find the probability that an x value is, say, less than A. Would you guys grant me that that is precisely this region over here? Okay? So, one of the types of curves that is discussed first and foremost is called a standard normal curve. And I only bring this up because some calculators only can compute in the standard normal situation. For example, mine. But some of you guys will have a calculator that can actually compute in any situation. So, it's a reasonable question. Okay, Lauren, what's the difference between a standard normal curve and just a normal curve? In a standard normal curve, your mean is always 0, and your standard deviation is always 1. That's all my calculator can do. But don't worry, we have a way around it. Okay? So, obviously this is not heights or weights or IQs, right? You're not going to have your average IQ be 0. That would be a problematic situation. I'm not a fan of IQ tests anyway, not that you asked, but so, here's our mean equal to 0, and our standard deviation is 1. Okay? Now, when we're in our standard normal curve, what we do is we refer to any point along here as a z-score. Remember, z-scores are precisely how many standard deviations away you are from the mean. Now, I'm going to take a little break for a second and go back to something that you guys probably learned in algebra at some point, and I'm about to have you refresh your memories. You ready? Do you guys remember your number lines? I hope so. All right, do you guys agree as you go to the right, your numbers get bigger, as you go to the left, your numbers get smaller? Okay? Now, what I'm saying here, you might be like, oh my God, why is she saying this and boring us to the nines? This stuff is going to be very pertinent whether you have a fancy schmancy calculator or one like mine. Okay? You may or may not remember something called interval notation. But if I wanted to express this interval right here, do you guys agree you could write it as -1, 1, and that expresses that interval? Do you remember that from an algebra class? Okay? Notice you always have your smaller number on your left, your larger number on your right. I am going somewhere with this, you guys. I'm not being irritating, at least intentionally. Okay? Guys with me there? Now, what if I wanted to express this region right here? There we go. Do you guys agree the way you would write that region there is, well, the smallest it can be is 2, and the largest it can be is you go off to infinity? Infinity is not a number, it's an idea. It just means it keeps getting larger and larger and larger and larger. Do you guys remember this? Okay? Why am I mentioning that? The reason why I'm mentioning that is we're going to want to get infinitely large and then again infinitely small. And when we do, we have to be able to somehow put that into our calculator. And there is no infinity button in your calculator. So the way you would do this, and you'll see where it's going, is you would put that 2, but in place of infinity, we tend to put 10 to the 99th power. 10 to the 99th power is a 1 with 99 zeros after it. Would you guys grant me that's sufficiently large? I would agree. All right. What if, on the other hand, I wanted to express this interval? Again, you always put your smaller quantity on your left. Isn't this going to negative infinity? And then we would put, say, -2. button here. So what you do is you put negative 10 to the 99, negative 2. Yes?
So is that for all the calculators or just?
It is for all the calculators. You are going to be punching in either positive 10 to the 99 or negative 10 to the 99. Now, what I'm going to do, we have 10 minutes, is really important, okay? Because this is the practical stuff that we're going to be using. And, or at least how to push the good old buttons on our calculator, okay? So, get out your calculator first off. And I will tell you how it will look no matter which type of calculator you have. If you do not have a calculator that computes the binomial distribution, you're not going to have one that computes the normal distribution. You need to get one. All right. So, ready? Here we go. Suppose you have a standard normal curve. Okay? Knee-jerk reaction. Mean is 0, standard deviation is 1. I like to draw pictures because I like an idea of what I'm looking at. What if I want to find, so this is 0, as you know. Pretend this is like negative 0.3, and this is 0.4. Again, it makes sense that it's negative to the left and positive to the right. What if I want to find the probability that a randomly selected data point falls between negative 0.3 and 0.4? Okay? Well, y'all ready to take out your calculator? Aren't we still dealing with the distribution? Yeah. You guys remember how we got to the distribution button when we dealt with our binomial? You do it the same way. You hit second bars, get to your distrit button, and now we're interested in normal CDF. All right. You all there? Now, your screen might look a little different. It might say lower, upper, etc., etc. That means you've got the nicer guide. Life is going to be a little easier for you than it is for me. Okay? If you have my type of calculator, you're going to have normal CDF. What you do is you put your smaller number to the left, your larger number to the right. This is why I went through this whole interval notation. If you have a fancy schmancy one, it's going to say lower. You're still going to put in negative 0.3. Then it'll say upper, and you're still going to put in 0.4. But yours will then also ask what your mean and your standard deviation are, and you'll put 0 and 1. Mine only can compute the mean and the standard deviation with 0 and 1. So I put in negative 0.3, comma 0.4. Now be sure when you put in your negative 0.3, you do not use your subtraction sign. Use your negative sign. At least on my calculator, it's the thing below the 3. And you get about 0.27. Okay? So, when the moral of this story right now is when you want to find the probability that a data point is between 2 points, all you have to do is put the smaller point on the left, or for the lower, your larger point on the right for the upper, go to town. You guys with me on this one? I have 2 more to do for today. Don't worry, this will be reinforced and it'll be second nature by the time class is done on Friday, for sure. All right, so let's pretend again we have a standard normal distribution. And now, let's pretend we want to find the probability that a randomly selected data point is greater than negative 0.55. Okay, pretend this is negative 0.55. Do you guys agree? I'm interested in the area from that on over to the right. You have to know your inequality signs. Okay, now, how do we do this in our calculator? And I will summarize this when we're done with these next two computations. You're still going to hit normal CDF. You guys, what is the smallest I'm interested in this being? Negative 0.55. Doesn't it go off to infinity? But in place of infinity, what do we put? 10 to the 99. So that's what I will put in my calculator. You guys with the nice ones, you're going to put lower is negative 0.55. Upper is 10 to the 99th power. You write it like that. And then, of course, you have your mean and your standard deviation, but right now those are not changing. So I have negative 0.55 and then 10 to the 99. And it's about a 71% chance. Does it make sense that it's greater than 50%? It sure does, because remember, 50% of your data lies above, 50% lies below, and we've got this 50% above and then some. Okay, you guys with me right now? We have one more to do. And I assure you class will be more fun on Friday, and the types of questions that you're going to be looking for are there. Let's do finally a less than, because we need to do that. Let's find the probability that a randomly selected data point is less than, let's just do -1. Wow. Okay, how would we enter this guy in? Well, if you were going to write that in interval notation, you'd write it as negative infinity comma -1. But we don't have negative infinity. So now what will you put as your lower? Negative 10 to the 99. And the upper will be -1. Or if you have my kind of calculator, you would enter negative 10 to the 99. You can't mess up the order, you guys. You won't get the correct answer. The sign will be wrong. And then -1, we get about 0.16. So, let me just summarize one thing here. Are you guys with me here? Okay. So, what I want to summarize, and again, don't worry, this is going to just be kind of the background of what we do here, is the following. If you want to find the probability that you're between 2 points, you do your normal CDF, and you put in those points. Again, if you've got the nice one, this would be lower, and this would be upper. If you want to find the probability that x is greater than some number, I'll call him, I'll just call him number. If you expect a W, you're going to be like XW. Oh my God. Again, you got normal CDF, you put the number and then 10 to the 99th power. Or again, if you've got the nice calculator, you put the number in the lower and the 10 to the 99th in your upper. And last but not least, if you want to find the probability that you're less than some number, it's still normal CDF, but now you have negative 10 to the 99th comma, that number. Or again, now this would be lower and this would be upper. Now we've learned